important model for the estimation of distributed lag model is the Koek model. Koek has proposed an ingenious method of estimating distributed lag model. We'll see the meaning of ingenious in the later stage. The way of calculation, the way of estimation, or the way of derivation he used is not a rational one. That is why it is termed as an ingenious method of estimating distributed lag model. And Koek used the infinite lag distributed model. That is, he used this model yt equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus ut. That is, the lag is not defined, and therefore he used the infinite lag model for the estimation purposes. And the estimation is based on certain assumptions, and it is given as follows. All betas have same sign. Here it is assumed that even though it is an infinite lag model, all betas have the same sign. Then second assumption is beta declines geometrically. That is, decline in beta will be geometrically, and he defined its geometrical decline as follows. That is, beta k equal to beta 0 lambda raised to k. This is the, and he defined the decline, geometrical decline as follows. Beta k equal to beta 0 lambda raised to k, k equal to these lags, where lambda lies between 0 to 1 and is known as the rate of decline or decay of the distributed lag. That is, the rate of decline or the decay of distributed lag model is given as lambda, and 1 minus lambda is known as the speed of adjustment. The speed of adjustment is given by 1 minus lambda. Then this assumption, that is geometrical decline of the betas or beta k equal to beta 0 lambda raised to k, postulate that each successive beta coefficient is numerically less than the preceding beta. This statement follows since lambda less than 1. That is, each successive beta coefficient is numerically less than the preceding one. That is, here beta 1 will be lower than the beta 0, beta 2 will be lower than beta 1, etc. That is, each successive beta will be numerically less than the preceding betas. This implies that as one goes back into the distant past, the effect of the lag on yt becomes progressively smaller. That is, if we go back, then the effect will become very smaller. The current and the recent past incomes are expected to affect current consumption expenditure. That is, the current and the recent past increase are expected to affect the current consumption expenditure more heavily than the income in the distant past. That is, current and the recent event, or in this case the income, I expect to have a higher impact on the consumption expenditure, and it is given here. Here the lambda is 1 by 4, then it will be 1 by 2 and 3 by 4, etc. That is, it declines geometrically. That is, here it is 0.75, 0.2, 0.5, 0.25. That is, it declines geometrically. As this figure shows, the value of the lag coefficient beta k depends, apart from the common beta 0, on the value of lambda. The closer lambda is to 1, the slower the rate of decline of beta k, whereas the closer it is to 0, the more rapid the decline in beta k. In the former case, the distant past values of the x will exert sizable impact on the yt, whereas in the later case, the influence on yt will peter out quickly. That is, the recent one has a higher impact on the yt. That is beta 0. Here the lambda is given as 0.75, then beta 0, then here there is no lag. Here the lag begins, and then here it is 1. The lag is 1, therefore beta 0 lambda raised to k will turn it into 1. That is, beta 0 lambda raised to 1 is beta 0 lambda raised to 1. That is, beta 0 into 0.75 raised to 1. That is 0.75 into beta. Here the lag is 2, therefore this equation is beta 0 lambda raised to 2, or beta 0 0.75 raised to 2. Then it will give 0.76. Then this will be beta 0 lambda raised to 3, and beta 0 0.75 raised to 3. Okay. Declines geometrically. Here also 25. Lambda is assumed as 0.25. The geometrical decline is given. By assuming non-negative value of lambda, Koek rules out the betas from changing signs. That is, he assumes that the lambda value of lambda will be non-negative or positive, and therefore he rules out the betas from changing sign. By assuming lambda less than 1, he gives lesser weight to the distant betas than the current ones. That is, by assuming lambda less than 1, he gives lesser weight to the distant betas than the current. He gives lesser weight to the distant betas than the current ones. He ensures that the sum of the betas which gives the longer multiplier is infinite. That is, sum of the multiplier sigma beta k equal to beta 0 into 1 by 1 minus beta is the long run multiplier, and it is finite. And these are the important features of the Coic model. These are the assumptions, and all the betas have the same sign. Beta declines geometrically, and that geometrical decline is given here. We used this equation for estimating that variable, that value in that table, and here the value lies between 0 to 1, and this means that the distant past values have lesser impact on the yt, or the recent values have higher impact on the yt, and this geometrical decline is given here, and the closer the lambda to 1, the slower the rate of decline, and whereas the closer it is to 0, the more rapid the decline in beta. And here the calculation of the lagged values for various lambda is given. Then the features are given here. Lambda, the features are given here. The beta won't change the sign because the value of lambda is positive. By assuming lambda less than 1, he gives lesser weight to the distant betas than to the current one, and the long run multiplier is a finite one, and the long run multiplier is defined as beta 0 into 1 by 1 minus lambda. In this section, the derivation of the Coic model is given. The derivation is like this. Yt, the model used for the estimation is infinite lag model. Yt equal to alpha plus beta 0 xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus ut, and he assumes that beta declines geometrically and the sign of betas will be the same. Beta k equal to beta 0 raised to lambda k. Now apply this equation into this model. Then we will get yt equal to alpha plus beta 0 xt. This such. Then this beta 1 will turn into beta 0 lambda raised to 1. That is, this beta 1 equal to beta 0 lambda raised to 1. That is written here, beta 0 lambda xt minus 1. Then beta 2 can be written as beta 0 lambda raised to 2. Here the k is 2. That k lag is given here, beta 0 lambda raised to 2 xt minus 2 plus ut. And the infinite lag model is given here as beta 0, and the infinite lag model is used for the estimation, and his assumption is that beta k equal to beta 0 raised to lambda k. By applying this into this model, we get this equation as alpha plus beta 0 xt plus beta lambda raised to xt minus 1 plus beta 0 lambda square xt minus 2 plus ut. And here the application is given here. Beta 0 equal to beta 0 can be written as beta 0. Here there is no lag, therefore lambda raised to 0. Lambda raised to 0 is 1, therefore it is beta 0 xt itself. Here beta 1 can be written as beta 0 lambda raised to 1. The lag is 1, and likewise beta 2 can be written as beta 0 lambda raised to 2. That is, by applying this one, we will get this equal. Therefore, the model is yt equal to alpha plus beta 0 xt plus beta 0 lambda xt minus 1 plus beta 0 lambda square xt minus 2 plus ut. This is the model. But this model is infinite model. This model is infinite model, and that is a large. But this model is infinite model. There is a large number of parameters to be estimated, and the parameter lambda in this model is non-linear also. Here the degree is 1, 2, etc. Therefore, it is non-linear. Therefore, the method of linear regression model cannot be applied in this model. Here, the parameter of lambda is non-linear. We can apply if the coefficient of the parameter is. We can apply the LS method only if the power of this lambda is 1. Therefore, he suggested an ingenious way of solution. Here, we used the term ingenious way. Take one period lag of this equation. That is, take the lag of equation number 3 on both sides, on the right hand side and the left hand side. Then we will get here yt is lagged, or lagged by 1 period, that is yt minus 1, then at equal to alpha plus beta 0, xt minus 1, xt minus 2, xt minus 3, ut minus 1. Then multiply the equation number 4 by lambda. That is pre-multiply the whole equation by lambda. We will get lambda yt minus 1, lambda alpha lambda beta 0 xt minus 1 plus beta 0 lambda square xt minus 2 plus beta 0 lambda cube xt minus 2 plus lambda. Then subtract this equation 5 from equation 3. That is, subtract equation this from this equation. Then we will get yt equal to alpha plus beta 0 xt plus beta 0 xt minus 1 plus beta. The equation. Now subtract the equation number 5 from 3. That is, this from 3, equation 3 is given here. Then we will get yt minus lambda yt minus 1, that equal to alpha minus lambda alpha plus beta 0 xt minus lambda beta 0 xt minus 1 ut minus lambda ut minus 1. Then we will get yt minus lambda yt minus 1 plus alpha into 1 minus lambda plus beta 0 xt plus ut minus lambda ut minus, the other terms will cancel out. Then this can be written as yt equal to alpha yt minus 1 plus beta 0 xt. Take this lambda yt minus 1 to this side plus vt, where vt is the moving average of the other term ut minus 1. Here in this equation, we have only 3 parameters, alpha, beta 0 and lambda, and it is highly linear. It is linear also, therefore we can apply the Euler's method for the estimation. This is the procedure given by the Koek. Once again we'll explain this. He used the infinite lag model, then applied this equation, then by applying this equation to the model, we used this method, apply this model. By applying this equation, we will get this model for the estimation. Then it is the equation number 3. Then since it is highly non-linear, Euler's method cannot be applied in this case. Therefore, he suggested some ingenious way of method for solution. And he first step, take the lag. Then second step, pre-multiply by the lambda. Then subtract that equation from this third equation. Then we will get the Koek transformed model, that is yt equal to alpha into 1 minus lambda plus beta 0 xt plus lambda yt minus 1 plus vt, where vt equal to ut minus lambda ut minus 1 is the moving average of the other term. And the features of the Koek models are given here. The features of the Koek models are given here. We started with the distributed lag model but ended with an autoregressive model because yt minus 1 appears as one of the explanatory variable. This transformation shows how one can convert a distributed lag model into autoregressive model. The appearance of yt minus 1 is likely to create some statistical problem. That is, yt minus 1 like yt is stochastic, which means that we have stochastic explanatory variable in the model, and the classical least square theory is predicated on the assumption that explanatory variables are non-stochastic. If stochastic are distributed independently of the distributed disturbance term. Here, the appearance of the yt minus 1 is stochastic. It is not stochastic. Then this is the second feature. In the original model of the disturbance term was ut, whereas in the original model the disturbance term was vt ut, whereas we transformed it into vt. The statistical properties of vt depends upon what is assumed about the statistical properties of ut, for as shown later. If the original uts are serially uncorrelated, the vts are serially correlated, and therefore we may have to face up the serial correlation problem in addition to the stochastic explanatory variable yt minus 1. That is, the first important feature is that we started with distributed lag model but ended with the O2 regressive model. Second one, the yt minus 1 is stochastic. That also creates problem. Third one, the error terms may be correlated sometimes. The fourth one is that the presence of lagged y violates one of the assumptions underlying the Durbin-Watson d-test. That is, presence of lagged y indicate if the lagged y values are present in this model, then we cannot apply the Durbin d-test. We have to apply the Durbin h-test. That is, in this case, in order to test the autocorrelation problem, we need to apply another test, namely Durbin Edge test. The reason is that the reason is due to the fact that in this model yt minus 1 or the presence of lagged values of the dependent variable arises. Some other important features are given here. These are the most important features, that is, we started with distributed lag model whereas ended with autoregressive model. Then the yt minus 1 is stochastic, that problem arises. Then sometimes the problems or the properties of the array terms in the last model, in the correct transformed model, also may create some problem. Then in this case, in order to test for the autocorrelation, we need to use another test, namely Durbin Edge test, or Durbin-Watson d-test is not applicable, as in this model lagged values of y are existing. The median lag is the time required for the from this we can calculate the median lag. The median lag is the time required for the first half or the 50% of the total change in y following a unit sustained change in x. For the correct model, the median lag is defined as follows: log minus log 2 by log lambda. Thus, if lambda equal to 0.2, the median lag is 0.46. Here, log 2 divided by lambda equal to 0 log of 0.2, that will be equal to 0.4630. If lambda equal to 0.2, then median lag will be 3.16. Verbally, in the former case, 50% of the total change in y is accomplished by less than half the period, whereas in the later case it takes more than 3 periods to accomplish the 50% change. Higher the value of lambda, the lower the speed of adjustment. This is the reason for that. In order to make this adjustment, it will take longer period. If the lambda is small, then the speed of adjustment will be high. The mean lag is given here. Mean lag is defined as sigma of 0 to infinity k beta k divided by sigma of 0 lambda beta k, which is simply the weighted average of all the lags involved in the respective beta coefficient, serving as the weight. In short, it is the lag weighted average of time. And in the case of the correct model, the mean lag equal to lambda by 1 minus lambda. Thus, if lambda equal to 1 by 2, the mean lag is 1. That is 1 by 2 divided by 1 minus 1 by 2. That is equal to 1.